Today I'm going to discuss about Newton's third law of motion. Okay, so first we have to know the statement. What is the statement? To every action there is an equal and opposite reaction. This is the statement of Newton's third law of motion. Okay, I think everybody you know this statement. Okay, now let me analyze it. First of all, you have to know what is action and reaction. Okay, action and reactions are nothing but two forces which act simultaneously when two bodies exerts force on other body. Just like this, here A and B, I consider two bodies. They constitute a system. There is no external net force acts on the system. Only the internal force exists. Okay. What are the forces? Here FAB. Okay. Look at the direction. Notice the direction. FAB is the force exerted by the body B on the body A. Okay. Similarly, FBA is a force exerted by the body A on the body B. Okay, here either of the force you can consider as action, so the other one should be reaction. Clear? That is, if we consider FAB is the action, so definitely FBA should be the reaction force. And according to the statement, we mathematically can express the third law as A vector, force is a vector quantity, you know, F vector AB, that is the force on A by B, and F is equal to FBA, that is force on the body B by the body A. Okay, here look at the negative sign here. That means these forces are oppositely directed. Forces are oppositely directed. And here the equal sign signifies the magnitude of the forces are equal. Is that clear? So this is the mathematical form of Newton's third law of motion. Okay. Now here I explain what is action and reaction. Clear? When a body exerts a force on another body, the force is called the action, and the same instant the second body also exerts equal force on the first body in opposite direction. This force is known as reaction. Clear? So here I take an example. Suppose an wooden block is kept on a table. So what are the forces acts here? One is the weight of the block, which is acting vertically downward. W is equal to mg. And other is the normal reaction by the table. Okay. Here it is N. So here I state this weight as an action. So definitely the normal reaction will be the reaction force. Clear? And according to Newton's third law, we can write N, that is the normal reaction, is equal to mg. That is, in magnitude they are equal. In magnitude they are equal. Okay, when I want to state the magnitude only, you have to put the force within this parallel bracket. This is known as modulus. Clear? Okay. Now, here some important point you have to remember regarding Newton's third law. First of all, action and reaction act on two different bodies. Okay. The forces are equal and opposite to each other, but they act on two different bodies. Okay, here you just notice the Example, here the weight acts on the table. Okay, weight acts on the table and the normal reaction acts by the table on this block. Okay, so action acts on the table and the reaction by the table acts on the body. Two different bodies. Okay. Number 2 here, the action and reaction always act simultaneously. Okay. There should not be no confusion that first action acts, then reaction comes. No. Both act simultaneously. As soon as action start acting, reaction also start acting at the same instant. Okay. Both are equal in magnitude and opposite in direction. This point already I discussed. And this Newton's law, this third law of Newton, you can use it for both contact and non-contact forces. You know, contact forces mean frictional forces. Okay, this push, pull, all these are the contact forces. Non-contact forces, for example, the gravitational forces, magnetic forces, electrostatic forces. In all these cases, Newton's third law is valid. Clear? Now come to the next part, conservation of linear momentum. Another very important topic for mechanics. So first we learn the statement. If no net external unbalanced force acts on the system of isolated bodies, then the total linear momentum of the system in a given direction remains constant. Okay. So Newton's second law we already discussed earlier. F is equal to del P del T. That is external force, external net force is directly proportional to the rate of change of linear momentum. Okay, here del P is the change in momentum. Del T is the time. So del P del T, this ratio gives the rate of change in linear momentum. For an isolated system, when no external force acts, so we can put F is equal to 0 in this equation. So what we get? The rate of change in momentum equals to 0. Okay. If you cross multiply, what you get? Del P, that is there is no change in momentum. Here you can write del P is equal to 0. That is no change in momentum. Del P means change in momentum. No change in momentum. Clear? That is momentum is constant. And you know, momentum is nothing but the product of mass and velocity. Okay? So mass and velocity remains constant for an isolated system of bodies if no external net force acts on the body. This is the conservation of linear momentum. Clear? Okay. So let me explain this conservation of linear momentum by some suitable examples. Okay. So we consider here two bodies having masses m1 and m2. m1 is moving with velocity u1. m2 is moving with velocity u2. Here the velocity of u1 greater than u2, they are moving along a same straight line. So definitely after some time they will collide because the velocity or speed of this body is greater than this. So they will collide. After collision, as they exert force on each other, the velocity of each of the body should change. So the velocity of the body of mass m1 becomes v1 the velocity of the body of the mass m2 is v2, and after collision let us consider the velocity v2 is greater than v1. Clear? So before collision, the total momentum of the system, you can write m1u1 plus m2u2. Before collision, the momentum of this body is m1 into u1, product of mass and velocity of this body, and this body, the momentum of this body is m2 into u2. So the total momentum of this two body system should be the sum of the individual momentum. Clear? Similarly, the total momentum after collision m1 v1 plus m2 v2. Here I mention this. Now, according to Newton's third law, during collision, if m1 exerts force on m2 is equal to F1, and the force exerted by M2 on M1 is F2, their action reaction pair. So we can write, according to Newton's third law, F1 is equal to minus of F2. Okay, and you know force is a rate of change of linear momentum, Newton's second law. So F1 is equal to change in momentum of the body M1, and here rate of change of momentum of the body M2, that is del P to del T. Del P, that is change in momentum, okay, of the body 1 M1. So M1 V1 minus M1 U1. Notice the figure. After collision, the momentum of the body M1 is M1 into V1. Before collision, it was M1 into U1. So change in momentum, definitely the difference of these two. So here M1 V1 minus M1 U1 by T. T is the time of contact of these two bodies during collision. Okay, that is the time duration in which the force acts on each other. Is that clear? Similarly, we can write the change in momentum of the body 2, M2, that is M2 V2 minus M2 U2. Clear? This T cancels out. And if you simplify, what you get? M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. What is this? This expression on the left hand side is nothing but the total momentum of the system before collision. Here this expression denotes the total momentum of the two body system after collision. They are equal. This is nothing but the law of conservation of linear momentum. Is that clear? Now here is some other two illustration of collision. I'm sorry, out of there is some illustration on conservation of linear momentum. So here it is gun and bullet system. Gun having velocity bullet having velocity u. Okay, when gun is fired with the bullet gets a velocity or speed is u, and because of that the gun experiences a recoil speed which is considered as v. Then total momentum after firing should be m into u plus capital M into v. M is the mass of the bullet, u is the mass velocity of the bullet, capital M is the mass of the gun, capital V is the mass of the velocity of the gun. Total momentum of the gun bullet system after firing. And before firing, definitely there is no speed of bullet. Bullet was at rest. So gun also was at rest. So total momentum before collision was before firing was 0. So from here you can find out the recoil speed of the gun. Okay. So this follows the conservation of linear momentum. Again, another example you can say is rocket motion and jet plane. Okay. During the firing of rocket, some gas is ejected from the back portion of the rocket with very high speed U. Because of that, the rocket gets a velocity in the forward direction, upward direction. This is also the conservation of linear momentum. Thank you.